Good morning, everyone. Today we're going to answer problem set 1, quantification theory number 5. I am Joshua JB Esteban, and this is the presentation of group 3. We're going to prove number 5, prove by contradiction. If there exists an x such that p of x is true, then it is not the cause that for all x, p of x is false. Now, in order to prove this, we'll use the statement and reason. The first statement is there exists an x such that p of x is true. We start by assuming the if part of the statement is true. This means there is at least one element for which p of x holds. And that is our premise. Assume the antecedent is true. Next is we have assume the conclusion is false for contradiction. For all x, not p of x is true. Now we assume the negation of the consequent is true. And this is the reason, this the assumption for the proof by contradiction. Next statement is we have for all, we can read this as for all x, p of x is false. Now this is the formal logic notation for the assumption in step 2. Now we have in step 4, applying the double negation rule on step 3, we simplify the assumption. This now means for all x, p of x is false. Now in step 5, we have not p of c for an arbitrarily chosen element of c. Since step 4 states that negation of p of x is true for all x, it must be true for any specific arbitrarily chosen element. And let's call it c. Now, in our statement 6, p of c is false. The statement negation of p of c is the same as saying that the statement p of c is false. Now, this is the definition of negation from 5. Now, let's proceed to statement number 7. From 1, there exists at least one element, let's call it uh, c sub 0, such that p c sub 0 is true. We return to the original premise, which is the step 1. The existence quantifier guarantees there is at least one element, and let's call it C sub 0, for which PC sub 0 is true. This is the definition of the existent quantifier from 1. In statement number 8, we have PC sub 0 is true and PC sub 0 is false. From step 7, we know PC sub 0 is true. From step 5, which came from the false assumption, negation P of C is true for any C. So we can substitute C sub 0 for C, meaning negation PC sub 0 is true or PC sub 0 is false. And that is the conjunction of 5 and 7 substituting C is equal to C sub 0. Now in statement number 9, which is contradiction, P of C sub 0 and not PC and not P of C sub 0. Now in step 9, step 8 states that a single proposition PC sub 0 is both true and false. At the same time, this is a logical contradiction, truth and false. As you can see in the reason, step 8 is a contradiction of the law of non-contradiction. And statement 10, we can conclude that the initial assumption 2 must be false, so the conclusion is true. Since the assumption that the conclusion was false led to a contradiction, a logical implausibility, the assumption must be false. Therefore, the original conclusion must be true. So in statement 11, we can say that if there exists an x such that p of x is true, then it is not the case that for all x, p of x is false. This is proof by contradiction from 1 to 10. The proof, and now the proof is complete. Thank you for watching.
Good day everyone, I'm Kevin, and now we will prove one of the items in problem set 2, which is the item 3 for our M216 logic in set theory. So we have here, let F has an elements 1, 2, 3, and 4, implying A, B, C, and D. Be defined as F1 is equal to A, F2 is equal to B, F3 is equal to A, and F4 is equal to D. And we are asked to determine whether it is adjective or surjective. For our proof, we have to test the item for injectivity and surjectivity. For injectivity, it states that if the function x sub 1 is equal to function x sub 2, then x sub 1 must be also equal to x sub 2 to be considered as injective. And for subjective, it states that every element of the codomain has at least one permeage in the domain. In our item, it is given that the function 1 is equal to a, and the same goes as function 3. But we also know that 1 is not equal to 3. And by transitive property, we also know that function 1 is equal to function 3. Thus, it violates the test for injectivity. Therefore, the item is not injective. And then let's proceed to another test, or the surjectivity test. We are given that the codomain are the elements a, b, c, and d. Also, we are given that function 1 is equal to a, function of 2 is equal to b, function of 3 is equal to a, and the function of 4 is equal to d. But as we can see, c was not an element of f, or in other words, the output c was not used in the function. Thus, it also violates the surjectivity test. Therefore, the item is also not surjective. Therefore, the item is neither an adjective nor surjective. That's all. Thank you.
Good day. I'm Cabaluna, and today I'm going to present a somehow a proof to one of the problem in problem set 3, axiomatic theory, ordinals, and cardinals. So I have here a problem using the von Neumann construction. List the four natural numbers and explain why each satisfies the definition of an ordinal. Now here's the first four natural numbers. In von Neumann construction, by definition, 0 is equal to empty set. And the uh, to get the 1, 2, and 3, the value of those, we need to use successor. Now by the definition of successor, if we have A, successor of A is equal to A union the element of A. That's why in 1, if we get the successor of 0, we have an empty set union set of an empty set is equal to a set of an empty set. And then to get 2, we need to get successor of 1. And to get 3, we need to get the successor of 2. Now, since we already listed the first four natural numbers using the von Neumann construction, we're going to determine, or we're going to check if each natural number satisfies the definition of an ordinal. That first, let's define, or what are the characteristics of an ordinal. A set is considered as ordinal if it is a well-ordered set and it is transitive. A well-ordered set, a set is a well-ordered if its non-empty subset contains a least element. Now let's proceed and check if 0 equals empty set is an ordinal. Is it well ordered? Well, 0 doesn't have any subset. Now this makes the condition vacuously true. That means 0 is considered as well-ordered set because the sufficient of the what I mean is that if the antecedent is considered as false, then the whole implication is considered as vacuously true. Since an empty set doesn't have any non-empty subset, which makes the antecedent false, then by the vacuously truth, 0 is considered as well ordered. Now, is it holds transitive property? Well, an empty set doesn't have an element. So, still, it is transitive by vacuous truth. Hence, 0 equals an empty set satisfies the definition of an ordinal. Now, for the 1, or the successor of 0, is it well ordered? Well, its non-empty subset is a set of 0 and 0, and it has a least element which is 0. Therefore, it is a well ordered. Now let's check if it holds transitive property. Well, the set has an element 0 and 0 has no element. So that makes the sufficient of the if-then statement of the transitive property vacuously truth. Hence, 1 satisfies the definition of an ordinal. Now for the 2, or the successor of 1, it has 3 non-empty subsets and each non-empty subset has a least element. Therefore, 2 is a well-ordered set. And also, it holds transitive property. Hence, 2 satisfies the definition of an ordinal. Now for 3, or the successor of 2, it has it has 7 non-empty subsets, each of which has a least element. Hence, 3 is a well-ordered set. And does it hold transitive property? Well, 2 is an element of 3 and 1 is an element of 2. By transitive property, 1 is an element of 3. Similarly, if 0 is an element of 1, so 0 is also an element of 3. Thus, the transitive property holds. Therefore, 3 satisfies the definition of an ordinal. Now, for the 4, or the successor of 3, it has 15 non-empty subsets, and each of which has a least element. Hence, 4 is a well-ordered set. And also, it holds the transitive property. Therefore, 4 satisfies the definition of an ordinal. And that ends my part.